so far we've already established that if you want to select a bunch of things and you want them in order, right? Firstly, we gave that a special name. We called them permutations. If you have n objects and you have k spots to fill, so you want k of those objects, right? You got two situations. You either got with replacement or without replacement. But we've noticed like that if they're objects and you're putting them into spots, then far and away the more common situation is without replacement. Like I can't put this pen in another spot once I've put it down. Okay. So then we developed this formula that had to do with factorials, right? And we called it NPK, right? And even though the reason why we use this NPK notation is so we don't have to worry about the factorials, it's still important that you get what it actually is. What's the fraction? What's on the top? N factorial, good. And then we're dividing by n minus k factorial, right? Why is it n minus k? Why is it n minus k? So the idea was you had your spots. By the way, I keep doing this. Good morning. I hope you're not getting sick of it. It's such a useful tool. Like 9 times out of 10, when someone has come to me, as you're working along, you're like, I have a question, right? 9 times out of 10, my explanation begins, well, think about, and then I draw this either on the board or in my head, right? Because it's just such a useful way to work out what's going on and why is my answer wrong, okay? So, you start off with n different choices because that's how many objects you've got to choose from, right? Say 10, right? And then you go, well, 9, and then 8, and then 7, and then the thing you have to divide by, the number of factorial that's missing, is n minus k factorial. In this case, I guess it would be 10 minus 4, which is 6 factorial. So we're okay with that, right? Now, the examples we looked at where order matters, right? What were the examples we looked at? Things like a password. The order kind of matters in a password. Other things like, say, a trifecta. First, second, third. Those kinds of situations, order matters, okay? But lots of the time, and remember, we're in the context of probability, right? Lots of the time, order does not matter, okay? So here are my counter examples. If you are selecting a team for a sport, right? I mean, just don't worry for a second about sports where positions matter. I'm just like, which 4 of you are going to be on this team? And which 4 of you are going to be on that team, right? Teams, the order doesn't really matter all that much. I just want to know who the people are, okay? Or committees, right? Everyone's going to be the same on this committee. It doesn't matter which order you get picked in, okay? And when we're thinking about probability, for example, consider a question like, a coin gets flipped, right? So we've looked at these and we drew probability trees or dot diagrams and so on. And one of the classic questions would be, okay, what's the probability that you get one head and one tail, right? If I flip twice, okay? Now you don't care whether the head comes first or whether it comes second, right? Head tail and tail head are the same with regard to which ones you're interested in, right? So in lots of situations related to probability, we're in this kind of camp. We're not in this camp. We don't worry about order, okay? So therefore, in unordered selections, how can we relate this to what we already know, okay? Well, let's think of this example here, okay? So suppose 10, 9, 8, 7, well, okay, no, let's make it a 0. There's a password, okay? So I've got a password there. Now, if I don't worry about the order, okay, that means that if I swap some of the numbers, okay, for example, if instead of this, I have, let's switch those two. If those are the same, right, it's the same selection without worrying about order, okay? You can see that there's going to be more than 2 ways to rearrange these same 4 numbers, right? And it'll be the same set of 4 numbers, just in a different order, which I don't worry about. Now the question is, how many? How many different ways can I rearrange these 4 and I'll still have the same 4 numbers? The answer is 4 factorial. It's 4, pick 4, right? So hold on a second. If I come to you with all of these different permutations, we already worked out there are 10,000 of them, right? and I say, look, here are my 10,000 different passwords. And you start to flick through, you start to look through the list, and you're like, hold on, this set of 4 numbers, you don't care about the order. This set of 4 numbers is the same as this one, which will be the same as, if I switch these 2 numbers, or switch these 2 numbers, and you'll be like, look, there are 4 times 3 times 2. There's like 24 passwords, sets of 4 numbers that are all the same, right? And you repeat it every time you get a new set of 4 numbers, right? I go 1, 2, 3, 4. There will be 24 of my permutations that for your intents and purposes, I don't care about order, they'll all be the same. There will be another 24 of these, and another 24 of the next set. So I've overcounted. How much have I overcounted by? I've overcounted by that 24, that 4 factorial, okay? And obviously if I had a 5-digit password, there would be even more ways for me to rearrange these, and you don't care because you don't care about the order, okay? So therefore, if I don't care about the order, if all I want to do is combine them in some sort of way, and that's what this is about. This is our counterpart to the idea of permutations where order matters. Combining, the picture I have is like in a recipe. Combine all of the wet elements in a bowl. You don't care where they go, you just chuck them all in, okay? If I don't care, then I've overcounted. This thing is wrong. It gives me too many, okay? So the number of ways will start with NPK, but I have to divide by something, right? Now in this case, I divided by 4 factorial. Why did I divide by 4 factorial? Because that was the number of ways I rearrange, and you're like, I don't care. Just give it to me, just give me the numbers, I don't worry about the order, okay? I overcounted by 4 factorial, that's the number of spots I have to put them in, right? That was K, that's why it's 4 factorial, it's K factorial. So I've overcounted by that factor. Does that make sense? So that's how we go from my list where I care about order because I'm OCD, to your list where you're like, I want to know which numbers they are. Order doesn't matter. So therefore, of course, you can go back to this factorial notation and you can say, sorry, I've run out of space, so I'm going to do something naughty and go across the board. You got this guy, n factorial on n minus k factorial, and then you're going to divide again by k factorial, and that'll fix you up. Okay, now I don't mind about the order. Okay, now just like NPK, this is a really important and very common scenario to worry about, right? And so that's why it gets its own notation, which we've already developed before in a completely different context. Okay, but this is NCK. By the way, the C stands for combination, and the P stands for permutation, right? But because combination and permutation are long words to say, that's why we often say n pick K and n choose K, even though that's a complete coincidence. No one designed it with that in mind. They designed it with these words in mind, okay? But you'll hear people say it like that.